Hi guys, let's solve today's Leetcode problem, which is problem number 1371, Jump Game 7. Okay, it's a medium problem. Let's read this out. You are given a zero index binary string S and two integers minJump and maxJump. In the beginning, you are standing at index 0, which is equal to 0. You can move from index I to index j in the following condition is fulfilled. Okay, what is the condition? I plus minJump is less than equal to j and is less than equal to minimum of I plus maxJump, comma s dot length minus 1. Okay, and s of j should be equal to 0. Okay, so if our j is within this range, I can make a jump only if this s of j also need to be 0. Okay, return true if you can reach index s dot length minus 1 in s, or false otherwise. So we have to start with index 0 and we have to reach n minus 1. Okay, if s dot length is n, so n minus 1 we have to reach. If it is possible to reach, then we have to return true. If not, then we have to return false. Okay, this is the question. Now let's see the constraint. So this s dot length is 10 to the power 5, which says that the brute force won't work, and s of I is either 0 or 1, and it is given that s of 0 will be always 0, which means we can definitely get started. Okay, now this min jump and max jump is again from 1 to s dot length only. Now, the approaches that we are going to cover as part of this question, one is we will solve this problem using BFS, and with BFS we'll do the brute force approach, basically the intuitive way that comes in our mind. And after that we will solve the problem in with BFS only, but optimally. Okay, we'll apply some optimization. Then another approach is using DP. So we will write the recursion relation, then we will try memoizing it. We'll see what works, what not works, and then final solution will be with the tabulation one only. Okay, so we are going to cover these things. Now, if we see this example, so here the minimum jump and max jump was 3. Now, in the first move, if we are from index 0, okay, if we move to index 3 like this, and in the second step from index 3 to index 5, we were able to reach, right? So from here, if we went to here, and from here, we went to here. So basically, we started from here and we were able to move there. So for that reason, we can return true. Okay. So same with this example, when we will try all the possibilities, even after that we will see that we are not able to reach from index this to this, with the range being this. Okay, so that is the question. Now let's check the BFS approach. One more thing before we started, we know that we have to reach this last index, right? N minus 1. Now let's say the last index itself is not 0, right? If it is 1, which means we cannot move, we cannot go there, right? So that can be our base case. If at any point, I mean, before starting, if we can check if this index n minus 1 holds the value 1, which means we can directly return false. Otherwise, we'll calculate whatever we are thinking to. Now, how we will solve this problem using BFS is we have to consider each index as node, okay, and each possible jump as the edges to that node index, okay. So from here, this our min jump is 2 and max jump is 3, right? And it was basically I plus this min jump and I plus max jump, right? So our j should be within that. So I is here 0, so 0 plus 2. Okay, and 0 plus 3. So within that this range we can jump. So which means I can jump to either 2 or 3. Okay, but 2 I cannot jump because the value is 1, right? So this jump is not possible. Now I can jump to this index 3. Okay, so what we will do, we will start in the normal BFS approach we will do. So first we pushed this 0 value into our queue. Basically the index 0 we have pushed into the queue, and we will explore all its adjacents or the neighbors or all possibilities, and accordingly we'll do. Okay, so initially we will push 0 because in question we have given this index 0 will always hold value 0. Okay, and we will mark the 0 node as visited. Okay, I have marked that as 1. So now we have to explore the neighbors of 0, so I'll pop the 0 out, and neighbors when I explore, I was able to go to 3, 2 and 3. Okay, and 2 I cannot go because the value holds is 1. Now I can go to 3, so I'll push the value 3 into queue and I'll mark this one also as visited. Now from 3, where all I can go, so it is 3 plus min value and max value, right? So 3 plus min, that is 2, and max value, that is 3 plus 3 6, which is outside of the bound, which means from here I can only go to 5. Okay, because if I go outside, this is out of bound, so I cannot go. So from here if I go, so I'll push 5 into the queue and I'll mark this one also as visited. Okay, now I explored the neighbors of 3, I took this out. Now for 5, when I see, when I reach this index 5, and this index is basically nothing but n minus 1 index, right? So which means I was able to reach this index, so I can return true. Okay, so this is the brute force approach for the BFS. So basically, at every index we are considering as node, right? So at every node we are trying all possible edges, basically trying out all possibilities, and exploring all possible edges on the way where s of j was equal to 0, and our j was within this range. Okay, so if that is possible, we will do. And we have also taken this visited array so that we don't revisit these arrays again and again. Okay, now at any point, if we reach this node n minus 1, we return true. Otherwise, after trying all possibilities, if we were not able to reach, we return false at the end. Okay, so that's about that. Now let's check the code for this. So this n is s dot size. Here the basic check, that edge case check, that if s of n minus 1 itself is 1, then we have to directly return false, because there doesn't exist any jump using which we can reach this n minus 1. Okay, now we have created this queue, and we have also created this visited array. So this visited array is initialized as false initially, and we have pushed this value 0 initially, and we have marked this node 0 as true, as above we did, right? Same things as above. Now we are iterating on this queue until queue is not empty, and this is the first node I, which is the queue dot front. We are getting out the node, and then we are popping that value. Now here we are checking at any point if our I, the current index that is there in the queue, the current node basically, if that is equal to n minus 1, which means we are able to reach this index n minus 1, right? So we return true. Okay, if not, then we will explore all the neighbors. And what is all the neighbors? So j was from I till I plus minJump, and j can go up to minimum of I plus maxJump comma n minus 1, right, as given in the question. So we will explore all these jumps which we can take. Now here we will check if s of j is equal to 0 or not, because we can make jump then only, and also if it is not visited. Okay, so that we don't keep on revisiting the same node. Okay, if that is the case, then we will mark this as visited and we'll push that value into our queue. Okay, so this is how we are going to do. And at the end, after exploring everything, if we are not able to reach, so we return false. Okay, so this was about the brute force approach. And if we see the time complexity, since we have this visited node marked, right, but still if you see that for any jump, for any index I, we can make a jump in this particular range, right? So this range can be big, right? It can be of length n, right? This range can be of in length n. Okay, so what we are doing for this, every I, we are checking all of this range every time, right? Though we are not pushing everything in the queue, because we have this visited array with us, so we are not pushing in the queue, but we are still exploring all the adjacents, right? For this I, we are exploring all its neighbors, and that can be up to length n. So this I itself can be up to n, and all the neighbors that we are exploring can be also up to n. So which means time complexity is nothing but O of n square. Okay, and space complexity, if we see, so we have taken this visited array queue and all that, so it would be O of n max. Okay, because in queue also we are not pushing, so at max it can be O of n only, nothing more than that. So that is about that. Now let's optimize this by the same means that that for every I, we are checking all of this range. Okay, so is this really required? We'll understand that. So the optimal way is basically same as above, whatever we are doing. So instead of processing all the nodes in the range, we will keep track of the last processed node basically. Okay, and we'll check for next nodes. Okay, we'll process from there. Okay, so what does this mean? I'll tell you. So let's say our index I, we are initially at index I is equal to 0, and minimum jump as 1. Okay, and max jump as 4. Okay, so with this, if I push this value I into my queue initially, right? So while exploring all the neighbors, we will scan all this, right? Basically, our loop will run for these values if we apply this range So our j will be from 1, 2, 3, 4, right? Using these values. So, and this will be pushed into queue as well because these were never visited. We started with index 0, right? Now we will take out 1 from this. Okay, our queue has all this value pushed. Now we will take out 1 from here. And for I is equal to 1, our range, that is again min jump and max jump, when we calculate, so our range will come something like, it will be from 2 to 5, which means the j value will go from 2, 3, 4, and 5, right? So when our I was 1. Now if you see, though we have marked these nodes as visited, right? If you see 2, 3, 4 here, we have added this value into queue already and we have already marked them as visited. Though while exploring all the adjacents, right, from there we are exploring these nodes again, though we will not, we will not process it, we won't process these nodes because these are already visited, but we are still scanning all the indexes in this range every time. So whatever the new range comes to us, we will again scan those every time. So this is for I is equal to 1. Now next value will be 2, right? So for 2 again we will have the range as 3 comma 6, right? Something like this. Okay, so again we will do all this range processing, where till 5 I know it was already processed, so the only remaining thing was there 6. Okay, so we need to only process for 6, not for remaining, right? So that is what the problem is, and how we will solve it, which is we will save the last processed node. Okay, so which will save us on these scans. So in this example, now let's say if we for while we explored for I is equal to 0, right? So we process till node 4, right? So we can keep this variable last processed node, okay, and we will keep that as 4. Okay, this is our last processed one. Now when we started exploring for this index I, we got this range value as 2 and 5, right? Now, what we will do, since we know that we have already processed, right? It is already marked as visited, it is already added in the queue. So there is no point revisiting those nodes, right? Though we will not add into the queue because those would be already visited, but no need of scanning as well, right? So what we can do, we can start our adjacent exploration from last processed index plus 1. Okay, so here last process index we marked as 4, so plus 1 will be 5. Okay, so we will this range we will run only for 5. Okay, so this and we, if you see also, right, this 4, 2, 3, 4 was already marked as visited, so we are not doing anything for those, we are only doing for 5. Okay, so this will save us this operation, and eventually if you see, right, altogether it will save us on so many operations. So this is what we are going to do. So this will significantly save us reprocessing of many nodes, and we will process each node only once. Okay, so this is the main observation over here. Now if we see, so s, the value s is given like this, min jump, max jump, again like this, we will push the value 0 here and mark this 0 as visited. Okay, now from 0 where all I can go, I can go to 3, 2 and 3, right? But 2 I cannot go because that is 1, so I'll go to 1. Okay, so 1 also, I'll sorry, 1 1 I mean 3, right? 2 and 3, so this is nothing but 3. Yeah, so 3 I'll mark as visited. Now from 3, since I know that while processing this range, our range came out to be 2 comma 3, right? So our last processed value was 3. Okay, so we'll mark this as 3. Now whenever the next value that we are going to explore, we will start exploring after 3. So when we started, so from 3, the range that comes to us is uh, that is 3 plus 2, right? So 5 comma 6, right? But this 5 is already greater than this last process value, so here it we won't, we won't be bothered because we can directly explore this value 5. Okay, in below example when we saw, it was last process index was less, right? So what we can do, we can basically take the max of these two values. Okay, the range, in this range, whatever the minimum value is coming and the last processed, whatever is the maximum one, we will start processing from there only. Since the maximum one here is 5, so we'll start with 5 only. So from here I can go to 5. Okay, I'll mark this 5 as a visited, and I was able to reach the 5, which is my n minus 1. Okay, so that is how it is. So that is the slight optimization here, but this is significant because it by doing this we are now processing each of this node only once. Okay, so now let's check the code for this. So the same things as above. Okay, it's actually I've copy pasted the same code from the above. There are few modifications, I'll just point to those modifications only. So we have taken this last processed value. Okay, last process node as 0 initially, and we need to know this range, right, every time. So instead of having this range we are calculating beforehand, the start value as max of I plus minJump comma last process node plus 1, right? So above I explained, right, we have to take the max every time of these value and the last process node, and end is nothing but the minimum of I plus max jump comma n minus 1, because we can go out of bound, right? That's why we take max minimum of n minus 1. Okay, so these are the two start and end value that we have calculated, and we will use the same in this loop also. So our j will start from s start, and the start we have taken the optimized values. Okay, and it will go up to end, and we will do the same processing as we were doing. Okay, so this loop will be significantly reduced, and every time we need to update our last process node also, right? So what that will be, that will be the max of last process node comma end, because in this range when I explore this value, whatever this is, 1 2 3 4, right, 5. So now this is my new last process node, right? So I have to update with this value, which will be max of this value last process node of the previous one or the end of this range. So this is what we need to update. We'll update this every time, and after any of the exploration, if we reach this value n minus 1, we return true. Otherwise, after exploring everything, if we didn't if we were not able to jump to n minus 1, we return false. Okay, so that is about this approach. And if you see with this, where we are now exploring only the newer indexes every time, and which is basically we are exploring only the new indexes, and at max we will explore all the indexes only once, which means our time complexity would be O of n and space complexity would be O of n, again for the same visited array and the queue that we have, right? So that is about the BFS approach. I hope you understood this. Now let's also understand the DP approach. So we will solve this using the recursion technique. I mean, to understand, right? Basically, looking at this, possibility, what first thing that comes in our mind is let's try all possible jumps. Okay, so our possible jumps were from j value being in the range, right? Something like this. So we will try all the possibilities of j, and while trying all the possibilities, we will check if at any point we are able to reach this value or not. And if we are able to reach, we can basically return true, otherwise false. Okay, so this is the same thing as in the BFS, right? So there, that is basically a BFS approach, and recursion is nothing but a DFS approach. So if I say it's more of doing the same brute force thing, so I won't do a dry run over here, but I'll just show you the code. Okay, how does the code looks like? So to start with, this is our can reach method, which has the string as min jump max jump and n dot size. This is the edge case that we have, and here we are calling this recursion function that we have written. Okay, so this s we have passed, and the index we have passed. Okay, so basically for index 0 we are basically checking if I start with this index 0, can I reach index n minus 1 or not. So this recursion will tell me if I can reach or not, and I'll return the same value. Okay, so yeah, now when I start from here, so this recursion, we are passing this by reference. This is important, otherwise we'll get, memory limit exceeded. So this is important to do that. Now, if I is equal to n minus 1, this is the base case. If we found this, then we can directly return true. Otherwise, this is basically trying all the adjacents, all the values for j, which is nothing but I plus minimum jump to minimum jump, minimum of I plus max jump of n minus 1. Okay, this is the value that we did above also, right, in case of BFS. And here we are checking if s of j need to be 0, then only we can make the jump. If it is 0, then what we will do, we will make another jump from that particular index j, right? So if this another jump also that we made from j, and if that was able to reach index n minus 1, which means that we are able to reach, right? So then we will return true. Otherwise, we will try all such j's, and for all such j's, we will keep on making this recursion call, right? And at the end, after trying all the possibilities, if we were not able to reach, we will return false. Okay, So this is how the recursion looks like. Now we can do a memoization over here, okay? But because if we see the time complexity for this, right? So this is exponential. Now let's say for every index I, what we are doing, we are checking all the j, right? So let's say the j, if the range of j on an average, let's say if it is something of k, so it is nothing but for every index I, we are making k possibilities. So time complexity is exponential, okay? And space complexity, if we see, so here we are not taken anything additional, but we still have this recursion stack space, okay? Recursion stack space. So that is about time and space complexity. Now let's memoize this approach, okay? So what we will do, we will store answer for the repetitive subproblems that we see, right, as we do in the DP also. So here what does the DP of I represent? This represent basically starting from index I. When we start with index I, can I reach index n minus 1? Is it possible? So this is what DP of I represent, okay? So if we are able to reach this index n minus 1 starting from this index I, then this DP of I will store value as 1, okay? Otherwise it will store the value 0, okay? So for converting this recursion to memoization, what we do, we create a DP array, and then we check before every calculation that we did in the above recursion, right? We check for each of the indexes and we store the values, right? Whatever we had, and we check if the value is already calculated, which means our DP of I already holds the value. We won't recalculate for that value, okay? So we will use the same value that is stored in the DP of I. So that is how the memoization will look like. Now, I mean, if I just try all possibilities in the example, it is same as the above example I illustrated above, right? So I will just make the code changes in the recursion, the same code as above, but we'll make some changes, okay? I'll highlight just those code. Now if you see, we have taken this DP array, and then we are having this check if DP of I is not equal to minus 1. So here this DP we have created, right? And here we have initialized the value as dp of n as minus 1, okay, initially. So this is the change. Now here we are checking if dp of I is not equal to minus 1, which means the value has been already calculated, so we'll directly return that value, okay? If not, then again same thing as above, we are exploring all the adjacents, and here dp of I is equal to true we are marking. And after this what we need to do, I mean, we are storing this value, right? Previously, in case of just recursion, we were returning true, but we are also storing this value so that we don't need to recalculate it again. And here also, we will store this dp of I is equal to false. So this is the only change in case of memoization code. So now if we see the time complexity for this, right? So this is the only change if you see. But the time complexity, it has not changed much. Okay. Initially, we were doing exponential calculation that basically for all the indexes, we are trying all possibilities blindly. Okay, so in case of recursion, that was the case. Even if you remember, in case of BFS, we had this visited array, right? So we were not blindly just doing the calls, right? We still had visited array, though we were exploring all the adjacent, but we had visited array, which was saving us some computation, right? But in case of recursion, we didn't had even that, right? So we were exponentially just doing. But here now, since we have the DP array, we are able to save on the blind calculation that we do. But even with the DP array, this is still not optimal, right? This is still not optimal. We are still exploring all the ranges, all the value in the range, okay? And while exploring all the values in the range, it can be the case that uh, while exploring all the values in the range, it can be the case that we are re-scanning all the values, just like above BFS thing, right? So this will again, give us TLE, because we are still calculating for all the all the values in the range. Okay. Okay. Though we have this DP array, we won't actually go and calculate the values, but we are scanning over those. Okay. This loop is basically scanning. So we need to stop that. Okay. we have to think on that manner, and due to that only the time complexity is O of n square. Basically for all this I, whatever possible j is there, I am going for all this j in this range, right? So this range can be up to n, and this I itself can be up to n. So time complexity is O of n square. And space complexity, if you see, so we have this dp array which will be of size n, so O of n. Okay, so yeah, that is about space and time complexity for this approach. Now since this will also not work because our n is up to 10 to the power 5, so O of n square is not going to work. Okay, so now we have to optimize this approach, and this can be done using tabulation plus some additional things. Okay, so we are going to discuss that in depth now. Now, in case of tabulation, what we do, we reverse the direction. Okay, so initially what we were doing, that we were going from index I. What does the dp of I represented there? That from index I, can I reach to index n minus 1? That is what dp of I was telling me there. But here, since we have reversed the direction, what does the dp of I tells? Can I reach index I if I start from index 0? Okay, so basically, if I starting at this index 0, can I reach this index I? Is it possible or not? Okay, we are just change the direction. Okay, and our j, where we were making jump initially, right? So it was I plus minimum jump till I plus max jump, all this, right? That was the our condition, because we were making the forward jumps, right? From I, we were going to all the forward jumps we were making, right? So we had this check that from what all jumps I can make, what all the j value can be there. But since we have now reversed the direction, what we are doing, for this I, we need to check all the previous j values, right? Such that from this previous j, am I able to reach this index I or not? Okay, for all the previous possible j's. So to reach I, there must exist previously reachable j. Okay, so there must be some previously reachable j exist. Okay, such that j should be within this bound. Okay, now how I came to this, I'll derive that formula, but this is how the reverse direction would look like. Now this is nothing but the backward thinking that we have. Okay, there we were moving forward. Now from here, when I am in this index I have to see that all this for any of these indexes I can come to this or not. Okay, now let's check the derivation. Okay, so this is the initial thing that we have, what was given to us in the problem. Now what we will do, that this minimum thing we have, right? This minimum was due to n minus 1, right? Because if I make I plus max jump, that can go outside of n, right? N minus 1. So for that reason, I needed this minimum jump. I'll leave that for now. Okay, I will add that later as per our need. Okay, now this is I plus min jump and this I plus max jump. Okay, this is what the new value is. Now if you see that if I move this I over from these side, both of the sides, right? If I move this I inside, so this is how it will look like. Okay, minimum jump j minus I. Okay, I move this I over here, from both the sides. So when I is the future position, from I we are going to the future position. Okay, so this was the case. This is the initial case, right? This is the initial condition that we are given, and this is what we are doing. We are going from I to all the future positions, right? Like this, from I. But our question, the direction and tabulation has changed, right? What we are doing now, from previous positions we are going to I, right? Now it is something like this, right? So what will happen, since this has changed, so this direction will also change, right? I mean, initially it was j minus I, but now it would be I minus j. Why? Because this, what is this j minus I? So we are at this I, and these my future positions are j, right? I am doing j minus I because j is my destination and this is my source. Okay, so that is why we had this j minus I, right? But here our I is the destination and these are the j value, which is source. Okay, so it is nothing but source minus destination, because jump length is source minus destination, right? So since our direction has changed, so minimum jump will be I minus j. Okay, so this is the change that we had to do in our formula. Now we will further derive it. Okay, so now what we will do, we will solve these inequalities individually. Okay, these two inequalities. So this is I minus j is less than equal to max jump. Okay, this condition that I have copied. Now, what I did, I moved this I this side. So it is minus of j and minus of I. Now, this is now if I do multiplication by minus 1, right? So what will happen? This minus j will become j, and you might have studied this in school, right? When we in inequalities, when we do multiplication of minus 1, then the sign symbol changes. So initially it was less than equal to, now it is greater than equal to. Okay, now when we multiplied this, so this minus I will become I, and this max jump will become minus of max jump. Okay, so this is how the derivation is for this one, the first inequality. Now the second part that we have, so this is minimum jump, this I have copied, minimum jump of is less than equal to I minus j. So what we will do, we will move j this side and I this side, remaining thing this side. So when we moved, so this was minus of j, it came this side is plus of j, and this is I as it is, and minimum of jump, if we move this side, it is minus of minimum jump, right? So this is the another equality how it will look like. Now if we combine both, this is how it looks like. Okay, I minus max jump is less than equal to j, and which is less than equal to I minus min jump. Okay, this was the derivation. Now we also know that initially we had this condition here, right? If you see, we were taking minimum for due to this n minus 1, because when we were doing plus of max jump, right, that can go outside of index, right? So we needed to take minimum over there. But if you know that now what we were doing, we are taking all the previous positions, right, of j, and we are taking I minus max of jump, and it can go outside of 0, right? So when it goes outside of 0, we need to take the max of 0 or whatever we have calculating. So this is the additional thing, as subtraction can go out of bound, so this is the additional max thing that we have to do. So this is our new formula. This is how we came up with this one. Okay, now, when if we come back to the problem, that is we are doing tabulation, that is changing the direction. Now, additionally, to solve this problem, just changing the direction is basically converting the memoization approach to tabulation, right? But our main problem was that we, for every index I, we are trying all the possible j's in this range, right? So that is our main problem, which was giving us TLE, right? So we are going to save on this. Now we'll see how are we really going to save on this. It is going to be using prefix sum. So what does dp of I represent? Basically, can I reach index I if I start with index 0? Okay, can I reach this index I? This is what dp of I represent. Is there any reachable index j in this range? Okay, so if I can reach to this index I from 0, if there is any reachable index j in this range, okay, if any reachable index j if there exists, then I can go to this index I, right? In other words, does there exist index j such that dp of j was true? Okay, and dp of j is equal to true means that index j was reachable to index I when it started with 0. Understood, right? So we have to find if there is any reachable index j in this range. If it is, then we can reach to this index I starting from 0. Okay. So now to find this, that if there is any reachable index j in this range or not, what we can do, for every I we can check for all such j, right? And wherever this dp of j is equal to true, if that is true, which means we can mark our dp of I equal to true. Here we are checking, right? Such that dp of j equal to true. So we'll mark this as true and we will break. So this is basically again checking for all such j, right? This is basically of n square again, because we are doing the brute force way, right? We are checking for all such j's like this. But now the optimal way is basically we don't really care by which j we reach this index I. We just need to know, can we reach this index I or not, when if we start from index 0, and that can be via j, right? Some, if there is any reachable index j there or not. Okay, if there is a reachable index j, what does reachable index j means? Which means that this j was an index which was reachable starting from index 0. Okay, if j was reachable, then if I have to reach this index I can reach to this I from 0 via j, right? So that is what it is, and we don't really need to care by which index j we are able to reach this I. We just need to we just care that, thus this at least there does there exist at least one reachable j exist or not. Okay, so this is nothing but a range query, right? So this prefix of I, what will this represent? Number of reachable indexes from 0 to I. Okay, so number of reachable index from range 0 to I, this will store number of indexes. So this is nothing but this dp of 0 plus 1 plus up to I, right? Why? Because dp of 0 tells me if this index is reachable if we start from 0 or not. dp of 1 tell if this index 1 is reachable starting from 1 or not. dp of I tells me if this index I is reachable if I start from 0 or not. Okay, what does this tell? It is possible or not, which means only true or false, right? Only 0 or 1. And now this prefix of I means number of reachable indexes, right? Number. And it tells me if this is reachable or not, if this is reachable, or if this is reachable or not. So if this is reachable, then number of reachable index, if this is, then 1, if this is, then 1, like this, right? So we will this dp of I will be holding this value, and it will be basically number of reachable indexes. Okay, it will hold the count. Now how many reachable position exist up to I? This will what prefix of how many reachable index, this will what prefix of I will tell. Now if we come back to our original question, it was, is there any reachable index j in this range or not? This was our original question, right? That is there exist any index j which is reachable in this range or not? Which means, let's say our dp looks like this for a case, and this is our prefix array looks like. Okay, let's say we have calculated it, though it will be like on the way we are calculating and filling this value for prefix of I and dp of I, we will do this on the way. Okay, not like pre-filled values, but I am taking this example. Now here, now let's say our range is 2 comma 4. Okay, so in general, if you know, right, this is nothing but a prefix sum, right? Now if I have to know the sum for this range 2 comma 4, okay, so this index 2, 2 and 4, right? So I need to know, this will be nothing but prefix of 4 minus prefix of 1, right? I hope you understood this. So if I minus this value with this value, which is 3 minus 1, which is 2, right? Now if you see the this is in this range, right? And if you see in this range 2 comma 4, there are two indexes which are reachable uh, starting from index 0, right? So this count is coming as true. So that is what we needed to do. And with using this formula also, we will calculate this prefix of I every time, and we will keep on calculating the value for this dp using the same things as discussed above. So now let's check the code for the same. So now if you see the code, right, we have this index, I mean values n and all that. This is the edge case that we are taking every time. We have created this dp array and this prefix array, and we know that dp of 0 will be 1. Why? Because this dp, what does it tells? That is this index I reachable starting from index 0 or not? And I know that always index 0 holds the value 0, right? Which means this is always reachable. For that reason, we mark this value as 0. Now prefix of 0 is equal to 1, which means that the count of number of indexes through which I can reach this index, right? So count. So with 0, I can reach with index 0 itself, right? So for that reason, the value is 1 here. Okay. Now what I will do, I have calculated for the index 0. Now I have to calculate for the remaining indexes. Okay. So we will do the same. We'll calculate for the index starting with 1, and we'll go till n. Okay. Now we will do this. Basically, we can this make a jump to this index I from all the previous positions This jump is only possible, right, if this value is equal to 0. If this value is 1, which means this jump itself is not possible, right? So that is why we need to check if for this I, s of I is equal to 0 or not. Then only we will be able to make the jump. Okay, if that is the case, then we will calculate our range. So our left would be max of 0, comma I minus max jump, and right is I minus min jump. And this range value we have derived above, right? How are we coming up with this range? Now there is one more thing that we need to check, that I mean, we did range query, right? So we calculated our range, and one more thing, this right, we are doing I minus min jump, right? So we are here I, and we are saying that this will come from some this value here, and this value can be outside of 0. Okay, let's say our j is here, it can be -2 or something. So this jump is not possible from -2, right? It can be possible from 2 from 0 only, starting from 0 only, right? So for that reason we need to check if this right is greater than 0 or not. If it is, then we will calculate the if this is reachable or not. Okay, we need to know if this index I is reachable by any any j in this range. What range? This left and right range, if this I is reachable or not. And that is we did above using the above formula, right? So for this range, left and right, is if this index I is reachable or not. This is what we are calculating. So which was nothing but prefix of right minus prefix of left minus 1, right? But here one more thing is left minus 1 can be less than 0, right? So for that reason we need to check if left is greater than 0, then only we will do this. If not, then we will take the value 0 only. Okay, this will tell me if it is 0, if it is reachable or not. Additionally, it will also tell me the number of nodes which is with which that node is reachable. Though here we only care if it is reachable or not. Okay, so if the value is greater than 0, which means this node I is reachable, so the same we will store in our DP. Okay, that to this index I, we are able to reach this index I, okay, via this range. Now we have stored this value, and after all this we will update the prefix value also. So prefix value is nothing but whatever it holds the value till I minus 1 plus dp of I. Okay, because dp of I holds a new value, that was this index reachable for this index I. So to this index I, was it reachable? So this is what dp of I will tell me. Okay, if it is, then we will add that into our answer. So that is how we are calculating, and at the end we above we were making the recursion call for starting with 0, because our recursion meaning was different. Our recursion meaning here is, can we reach this index n minus 1 starting from index 0? And that is also on, that is the question, right? So that is why we will return this dp of n minus 1. Okay, so since we are not actually doing any calculation for all such j value, we are optimistically and optimally doing this range calculation using prefix sum. So for that reason our time has reduced drastically to O of n. And space complexity, if you see, so we are using this dp array and the prefix sum array, that is nothing of size O of n. Okay, so that is about this approach. I hope you understood, and if you like this video, thank you for watching. Stay tuned for next videos.